Okay, so we're going to talk about a lot in today. So slope fields and what's known as Eulers Method. So as I just said a moment ago, we're going to revisit a little bit solving a differential equation. Then we'll talk a little bit about slope fields, and that will take us to Eulers Method, which is a new topic, a BC topic that we haven't seen and done before. So this was right about the time last year in AB last year where we went on spring break and never came back. So that was a long, and for some of us it was really a long spring break, if you know what I mean. Some of us struggled to come back to work and to do class, but that's a different topic altogether. So I'm not terribly confident in our depth of understanding on that. So this is one of those topics that, as we do our blitz review of Calc AB, that I think is worth spending a little bit of time on and making sure that hopefully we understand it the way we want to. So a definition. So make sure we're clear what we mean by a differential equation. So an equation containing a derivative. An equation containing a derivative is what we call a differential equation. And this is commonly abbreviated as DE. So we say it so much and we get tired of writing it all the time. So we'll call it a differential equation. I don't know if you have any older siblings or you know any brilliant students that have gone on and taken beyond calculus in college. There are what are known as ordinary differential equations and what are known as partial differential equations. So if you know somebody that's an engineer or a math major, then they talk in their own language, and you might have heard them talk about ODEs or PDEs, and that's what they're referring to there. So we are in AP Calc AB and BC. We will talk about solving what are known as separable differential equations, and that's all we will try to solve, although we will talk about slope fields and use Eulers Method on some differential equations that are not separable and try to talk about what we know about the solution or how we can approximate a solution. But there are many, many different kinds of differential equations, and it's a rich and deep topic subject, and it's you can take several undergraduate and even graduate level classes on solving differential equations. So it's an applied math topic. That is, ordinary and partial differential equations are used to solve real life problems, and we'll show a little clip from Hidden Figures here in a moment where they're talking about one where they're trying to send somebody out into outer space, and they have to solve some differential equations, and they can't figure out how to solve them, and so I'll let you see it. I don't want to take all the fun. So those are known as differential equations. The order of a differential equation is the highest derivative involved, is the highest derivative, I'll say, that appears. So there are several different ways of classifying differential equations, and if you ever take an undergraduate differential equations class, what they do is you try to classify the differential equations, and it's kind of like each class of differential equations has a different strategy for how you solve that kind of differential equation. So one way of classifying them is by the order, the derivative. So if we have something like, say, dy dx is equal to secant squared x plus 2x plus 5, then that's known as a first order differential equation because it only has a y prime in it. A first derivative is the highest derivative. It's also known as an exact differential equation because you just have the derivative equals blah, blah, blah. There's nothing else to do for that. So this is in a sense about as simple as you can get in terms of differential equations. If we have something like, say, y double prime minus y prime is equal to 5y, then here the highest derivative that appears is a second derivative. So that would be known as a second order differential equation. That's one way of classifying that. So we can, in the case of the one that I gave you here, we can solve this because it's really just a matter of integrating both sides. Because you have a derivative on one side and you have a function of x on the other side, and we can do that. So the integral of the derivative is just a function of y, and then we take the integral of the right side, and we know the integral of secant squared is tangent x, and we know the integral of 2x is, and the integral of 5 is, and then we get a plus c at the end, the constant of integration. So what you see, you can kind of tell right here, because of this plus c, when you solve a differential equation, you get this family of functions that are the solutions. So this is an infinite number of solutions that are all, in this case, not always vertical translations, but these are just vertical translations of each other. You know, pick a different c, and it's just going to be a translation of what you get with a different value of c. And so this is known as a general solution. So it's that family of functions that solves the differential equation. And so if we add what's called an initial condition, if we know the value of the function at a point, and you know, sometimes we need more than one initial condition, because if we have a first order, we're going to integrate once, and we're going to get one constant of integration. So we're going to need one initial condition. How are we going to decide what that c is? If we have a second order, somehow or another, we're going to have to integrate twice. And so each time we integrate, we're going to get another constant of integration. So we would need at least two initial conditions in order to determine specifically what that particular solution is. So it's just more language and vocabulary here. So the differential equation together, wait, hold on, stop. I skipped a part there. Hold on. Let's say to find a unique solution. So to find a unique solution from our general solution, more information is needed. And I'm just going to say, I'm going to shorten this out. These are known as initial conditions. So sometimes you might know the value of the function itself. Sometimes you might know the value of the function and the value of the derivative somewhere, or sometimes even more information than that. So together then, that unique solution, so the unique solution satisfying the differential equation and the initial conditions is known as a particular solution versus a general solution. And the whole thing together, the differential equation together with the initial conditions, is known as an initial value problem. That's not really as big a deal for you. I think that's more a calculus teacher kind of thing that would be used in calculus teacher circles. So, for example, if we have dy dx dy dx is equal to e to the x minus 6x squared. And we have the initial condition 1, 0. And we find the particular solution. So can we find a function that satisfies the differential equation and contains the point 1, 0? Yes, we can, is the answer to that. So let's do that. So we can just integrate both sides. I got the left side. On the right side, the integral of e to the x is, and the integral of negative 6x squared is negative 2x cubed, is that right? And then a plus c. And so then we'll plug in the initial condition, so 0 goes in for the y, and we plug in 1 for the x. And so we get kind of a strange looking c. C is going to be 2 minus e. Good. You okay with that? And so then our solution, so the solution to a differential equation is always a function. Okay, so the solution is the function e to the x minus 2x cubed, and then our plus c is the plus 2 minus e. Okay, good to go? Okay, so talking about slope fields now. So we're going to change gears here and talk a little bit about slope fields. So, and we have, I'm just talking to the video for a minute here, we worked on a little worksheet to make some slope fields. Katya in particular found this very satisfying, and she asked for some more problems that she could do just because she so enjoys making slope fields, and I do have more that we can do if you'd like. So, but anyway, I digress there. So what we can see from slope fields is some different solution curves. So for example, and I don't have mine filled out, so I'm going to take a peek at somebody's here. So on that first one, yeah, so on first one, yeah, that's all I need was to look at it. So the first one we filled out, you get something that kind of looks like this, kind of just, so the little pieces of tangent lines that you have drawn there kind of look like they're forming a circle. So remember that now what happens is we can tell what a solution curve looks like depending on what the initial condition is. But remember, a solution to a differential equation is a function. So a solution to this differential equation is not a circle, because that would not be a function. Okay, so in fact, a solution to this differential equation, what was it, dy dx is? Negative x over y. So you can see that it's going to be a semicircle, right? You're either going to get the top half of that semicircle if your initial condition has a y value that's positive, because it's going to take you somewhere there. And if your initial condition has a negative y value, you're going to get a semicircle that's in the bottom half, just down here. Okay? It couldn't be a semicircle that's like sideways or this one, because it's got to be a function. And it's got to be a continuous function also. So a solution to a differential equation is only good on a continuous domain. Sometimes you will see from your slope fields something that might look like it suggests, you know, I'm trying to imagine, you know, you get a slope field and maybe it's looking something like that, where it's suggesting that you have a vertical asymptote right over there. Well, now what happens is if you get an initial condition over here, it's only going to be valid up until you get to that vertical asymptote, because that's a discontinuity. it's not valid over there. So you need a different solution with a different initial condition once you hit a discontinuity. So a solution to a differential equation is only valid on a continuous domain. Okay? So now, and then if you do have, suppose we just got an initial condition, say there, when you try, so a lot of times you'll be asked to draw a solution curve that satisfies that initial condition. So try to just go with the flow. It's not intended to be like a connect the dots thing. You know, it's because remember what we're seeing is that each of these is a tangent line to the solution curve at a particular point. And so you would just kind of, you know, eyeball it and say, oh, it's going to be some semicircle that's going to go through that point.
That was really good.
Thanks. I might leave that one up there. Okay? Questions on that? Now, sometimes you'll be given, and they like to, on AP questions, we may look at some of these down the road. I think you'll see some in your homework, where they will give you kind of like a multiple choice matching kind of thing, where you'll see several slope fields and have several different differential equations, and you try to match them. Now, solving the differential equation is not the way to do this, because usually what they'll do is they'll give you ones that are not separable, and so we can't solve them anyway. And so you can spend a lot of time spinning your wheels trying to solve a differential equation that we can't solve anyway. Instead, you look for kind of hints. You know, one thing to look for is where will we get horizontal tangent lines? Where is the derivative equal to 0? And in this case, you could see that it would be equal to 0 wherever x is 0. And so x equals 0 is that vertical line. So you would look for where do we get a slope field that's got horizontal tangents along the y-axis. Where is it going to be undefined? Well, it's going to be undefined when y is 0. What does undefined look like in terms of a slope of a tangent line? It's going to be vertical, which they may or may not show, you know, so you would look for something like this, or it may be just that they don't actually show those because it's actually undefined, but it's approaching that as you come into those points on the y-axis. Other things to notice is, you know, if you get a slope field that does something like this, where you see that all along this horizontal line, they're always the same. So as the y's change, this gets flatter or steeper, but as you go right to left, they don't change. So it doesn't seem to matter what the x value is, but it does matter what the y coordinate is. Then you would look for a differential equation that doesn't have an x in it because it's unaffected by the x. Does that make sense? And so, and you can even sometimes look, you know, like what's happening in different quadrants. You know, do the slopes all look like they're positive here? Well, then it could have an x and a y, but not a negative x, y. And so those are kind of things we can do to get information about the slope field and the solution curve. Okay. Well, I would like to talk about Eulers Method. And then we'll watch this motivating clip. So Eulers Method, we're going to use linearization to piece together tangent line segments to build a continuous approximation to the curve that is a solution to, I'm going to say, an IVP, an initial value problem, a differential equation with initial condition. So the idea is that many differential equations we can't solve. Not just us, but nobody can solve them. But they need to be solved. So if we can't solve them, kind of like what we did with, trapezoidal rule and Simpson's rule, if we ran into an integral that we couldn't solve, we couldn't find a function that was a closed form solution to it, we tried to approximate the area under the curve.
What do you mean, like we can't solve it?
So it means that we don't have a technique that will allow us to come up with, here's a function whose derivative is this.
Like, can you give an example?
I don't know enough about differential. I can give you one that we can't solve, and so we can imagine that what we know is all there is that's known about differential equations, which is far from true. But if we have something like, say, dy dx is equal to x plus 1. So that is not a separable differential equation. So remember, separable differential equations are things like, say, dy dx is equal to x squared y squared, where we can separate the y stuff times dy to one side and the x stuff times dx to the other side. And this is going to usually happen by multiplying or dividing. So we could, divide the y squared over to the dy side, multiply the dx to the x squared side, and we have separated the variables. All the y stuff times dy is on one side, all the x stuff times dx is on the other. Now we know how to do this. We can solve this from there. So this is a separable differential equation. This is not. So that we do not know how to solve this. This takes more knowledge of differential equations. We have to learn some other techniques, be able to try to classify it, and then maybe we can solve it. We can't. But there are others, like this is to us. I don't remember how to solve this. Maybe one time I knew, I don't know. So for us, this is unsolvable. Well, that happens to even the people that know all there is to know, all that is currently known about differential equations. This can happen. But what if we need to solve? These differential equations arise from real life problems because they talk about rates of change. Anything in the extractive industry involves differential equations. They're looking for methane or for gas, that's buried beneath the surface. Well, it flows through whatever the underground looks like, and so those are rates of change of liquids and gases and so on. And so those can be modeled by differential equations, rates of change. And so, it's used to solve real life problems. So what if, we have a differential equation, we can't solve it? Well, what Eulers method does is you can kind of see it like in a slope field, where you might see something, like that, it might do something like that. So we'll have, an initial condition, so something where we know a starting point, but now we don't know how to solve the differential equation. So what we're going to do is say, okay, we got the tangent line to the point, to the solution curve at that point. And we know there's a differentiable function, so we know that a tangent line is a reasonable approximation for a little while. And so we're going to build the tangent line to this unknown curve that we can't solve for at that point. And then we're going to kind of ride that tangent line for a little while and then see where that takes us. And now we'll treat that new point at the end of that little piece of the tangent line as a new initial condition. And so now we'll go back and say, okay, where's our differential equation? Find the slope, we know the point, we'll build a new tangent line. And so we'll kind of ride that tangent line for a little while. Not very far, because we know the longer we go, then the less accuracy we get. And then we'll see, well, what's that new point right there? And now we'll build a new tangent line. And so we do this over and over and over again, which, we're not going to do it very often. Like, we'll do like 2 steps, because it's the idea. Your book might ask you to do too many steps, 4 or 5, where it might get a little tedious, and I know how you feel about that. But an AP exam, they won't ever ask you to do more than 2 steps. Okay, so it's the concept that we're after. But you can see that we're going to do the same thing over and over again, which makes it very programmable, which means that you could put this into a computer that doesn't mind crunching numbers, And we could make those steps really, really small and do lots and lots of them and get a, the one that I'm drawing here is like the one we will be drawing is very segmented. It's like one of those jump ropes, that's got the little plastic segments. So it's not very smooth. But if you, take those segments and shrink them down, pretty soon it becomes really smooth and a nice curve, and it's going to be a better approximation. And with technology, you can do that. But we're just getting at the concept of it. So let me show you a little bit of this clip of Hidden Figures. So it's pretty fun, I think. And how many people have seen Hidden Figures? Anybody not seen it? Oh, yeah, great movie. Great.
Do we get to watch it at Christmas?
Yeah, you can watch it over Christmas. I think you can do
Well, we don't get to watch it as a class.
it. Oh, I'm not coming up here at Christmas to watch it, but you're welcome to.
That's what they did at the middle school every year.
Oh, really?
Orbit to a parabolic orbit. There's no mathematical formula for that. Because we can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong.
How's that?
Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Eulers Method.
Eulers Method.
Yes,
That's ancient.
but it works. It works numerically.
Kind of gives you goosebumps, doesn't it? I love that shot.
That's it.
Let's type it up.
Okay, so that's what they're talking about there is exactly what we're talking about now is Eulers Method. So let's see how it works a little bit. We talked a little bit about kind of the big concept that we're going to build tangent lines and connect them to make a solution to a differential equation. So let's say dy dx is going to be x plus y. And we'll say our initial condition is going to be f of 2 is equal to 0. And we'll say our delta x is going to be, say, 0.5. And we're going to approximate f of 3. So if you read the book and see how they propose solving this, they'll make a big elaborate table and write all that out. And that's the way I taught it the first couple of years when I did this. And then I got a chance to grade one of these when I graded some AP tests one year, we had a problem with Eulers Method. And they were so picky about what you had to have and label when you did it as a table that almost nobody that did it that way got the points for it, or at least got full points. And what I saw other people doing was just coming up with an actual tangent line at one point, and then using that tangent line to bump it up one, to put in x plus the delta x into the tangent line, get that new value of y, and then use the x plus delta x, y plus delta y as a new point, and then getting a second tangent line, and then plugging in a value of x plus delta x and getting the answer. And those people scored really well on it. And so I was like, From here on out, that's how I'm teaching it. And so if you were going to do this, you know, with 5 or 10 or 100 steps, you would want to make it a table and program it. But the idea that they're after in AP is just the concept. And they will never ask you more than 2 steps. So you can see that go from x equals 2 using a step of 0.5 to get to 3, it's just going to take us 2 steps. And so doing the tangent line, I think that's the way that I'm going to recommend you do it. So let's see what that looks like. So we're going to get our first tangent line. So this is tangent line number 1. So we're going to use our initial condition. So this is the point 2, 0. And that gives us the point, and the differential equation is where we're going to get our slope. And then we're going to make our tangent line. Does that make sense? So if x is 2 and y is 0, and our slope comes from dy dx equals x plus y, our slope is going to be 2. 2 plus 0 is 2. Is that okay? So our tangent line is going to be, you know, y minus 0 equals 2 times x minus 2. Did I do that right?
Yeah.
Okay, so there's our tangent line. We can go ahead. You don't have to, but this isn't too bad to just go ahead and distribute it out. So here's our first tangent line. Now we're going to take this tangent line and we're going to use it as our function curve, and we're going to go over delta x from where we started. So that means the value of x we're going to plug in here is going to be 2.5, exactly. So we're going to use x equals 2.5 and plug it into our tangent line to get what that y value will be. This is like taking f of 2.5, but we're using our tangent line as the approximator. So that means we're going to get y equals 2 times, we're plugging in the 2.5 minus 4. You still with me? And so that's going to be 5 minus 4, which is 1. So now we have a new point. We have our new x value, which was the x plus delta x, the 2.5. And we have our new y value, which is now 1. And so now we're going to build a new tangent line, our second tangent line, at this point. So now we've got tangent line number 2. And we got our point, which is 2.5 comma 1. And using that point with our differential equation is going to give us a slope here of, I'm going to write it out, 2.5 plus 1, the x plus y, which is going to be 3.5. Okay? Point slope, we write our tangent line. So it's going to be y minus that 1 is our slope, 3.5, times x minus 2.5 is our x1. And we can, you know, I guess we can multiply it out, or if you want, we could just plug in our x plus delta x now. I don't know what looks best to you. Just plug in. So our x was 2.5. We're going to get a new value of x, which is our x plus delta x, which is going to make that x be 3. So we're going to plug in 3 into our tangent line to get a new value for y. So we're going to get y equals, I'm going to add that 1, plus 3.5 times, and the 3 minus 2.5 is going to be 0.5. Am I going too fast there? You with me there? And so what's that, 1.5 and a 0.2, 1.75? Does that sound right? Plus the 1. So that's 1 plus 1.75, 2.75 sound right? And now remember what we did is we plugged in 3. We were using our tangent line as an approximation to the function. So we're saying that f of 3 is approximately 2.75. That's using Eulers Method to try to find the value of that. Does that make sense? Now, I mean, it's a good news, bad news thing. On an AP test, they would never ask you more than 2 of these iterations. So I think doing the tangent line really cements the concept of where is this coming from. Some of your homework problems may ask you to do 4 or 5 iterations, which it gets a little bit painful, I will admit to. No.
Complete 2 steps and then move on.
That would be a no. Okay, so let's try one. So let's do and we can come to the board if you like, or you can do it at your desk if you'd rather. So we're going to say dy dx is going to be 2x minus y. There's our differential equation. We're going to say that f of 1 is our initial condition. We are going to try to approximate f of 0, and our delta x is going to be a negative 0.5. So we can go either direction. That's kind of the point of this. So we're going to start at our initial condition here, and we're going to work our way from right to left. Hallelujah.
Oh, yeah, yeah. That was a weird thing to say, wasn't it?
Yeah, I know.
I might work. But like, I guess, like, yeah.
Are we reaching consensus here? We're going to get that f of 0 is approximately 0.25. Okay. How about if we're still working? We okay at the board? Rebecca, you okay? All right. Can we squeeze maybe one in real quick to see about the continue? No, we can't. No way. So I just want to see if we can talk about the continuous domain piece. So I'm going to, because I skipped over this one because I want to get to Eulers Method. So this is just a solving of a differential equation, and the solution is only valid on a continuous domain. So if we say, for example, dy dx is equal to 2x minus secant squared x, and our initial condition is 0, 3, then can we include the domain on our solution? So can you solve the differential equation, get the initial value, or use the initial condition to get the value of c, and then decide what is the domain of your solution? Apparently not. So, the idea is that we know what I was going to get to is a tangent has vertical asymptotes at negative pi over 2 and pi over 2, right? At all of the over 2's. So there are discontinuities for tangent x at every multiple of pi over 2, integer multiple of pi over 2. So since our initial condition has an x value of 0, that plunks it in between negative pi over 2 and pi over 2. Those are the two vertical asymptotes that will bound that domain. So you could plug in and find the c value. That's not the hard part. But recognize that this solution would only be good for a domain that would go from negative pi over 2 to pi over 2. So it's only valid on a continuous domain.
Do we need to finish it?
Yeah, I would like you to finish that and answer the questions at the back. Let's try to talk about that. Yeah.
Or are we supposed to?
You are supposed to.
Shouldn't have asked.